Okay, in this video, we are going to have a look at an automotive project. Now we're going to design and build a tachometer. Now that's a device that will display the RPM of a four-stroke engine. Now to do that, I first had to build an ignition simulator, which you can see here. Now this simulates the ignition system of a car that's running. So here's a coil, and it's connected to my spark plug. So if I energize it, you can watch the spark plug sparking. So the frequency of that spark is equivalent to a four-cylinder engine revving at 10,000 RPM. Now of course my four-cylinder engine is not going to rev that high, but building the tachometer, if it's picking up 10,000 RPM reliably, it'll work all the way down to idle. Now this tachometer is for the vintage cars, because the new cars have coil over plug. They have a coil for each spark plug controlled by the computer. So this tachometer is for the vintage cars that have points and condenser and a distributor and a coil. Okay, here's your typical ignition coil in a vintage car, and you can see the two terminals. That's your primary side. So this side marked plus is connected to the 12-volt battery, and the minus is connected to the points. So the points would ground this for the dwell time, and then when the points open, we'll get a spark, and that comes out of the secondary, which is in the middle of the coil. Now this is fed to the distributor. Now distributor has a center connector where the coil is connected. Then inside is a rotor that distributes the spark to all the spark plugs. Now this is for a V8, but the car that I'm going to design my tachometer for is for a four-cylinder. So that's your vintage ignition system. So we'll build a tachometer that'll read the RPM of a four-cylinder engine. Okay, there are two ways in which we could hook up our tachometer circuit to our ignition system. Now the first way is inductive. You see I built an inductive sensor. I got some hookup wire, 4 turns around the cable coming out of the coil, and we could detect the pulses coming out of the coil. Now if we measure the time between the two pulses, we could actually calculate the RPM of the engine. Now the second way is directly connecting to the coil, to the negative side. That's the side that goes to the points, and we could pick up those pulses also, the same as coming out of here. And when we get the time between pulses, we could calculate the RPM of the engine. Okay, next we're going to have a look at the pulses coming out of my inductive pickup, which is some hookup wire, 4 turns around the spark plug cable coming out of the coil. So I'll energize my ignition simulator, and there's our pulses. So if we measure the distance between those spikes, it's very short, that's when it's firing, we could calculate the RPM of the engine. Okay, here's my breadboard with my tachometer circuit, and the reason why I'm making this video, I want to clean off this breadboard. I want to take off all the components, so I thought I'd do a video first to document it before I stripped everything off. Now when I work on my car outside, I don't want to bring out my bench scope or my bench power supply, so I have a portable scope, and this is my portable power supply. It runs off a lithium-ion battery in 18650, you can see here. It has a charging port, USB-C, and it will give me 3.3 volts and 5 volts, so that's pretty handy when I'm outside. So this is my circuitry here. So I have an opto-coupler, which is connected up to my inductive pickup, so it's totally isolated. Then I have a Schmitt-Trigger NAND gate where I'm cleaning off all the signals. Then I have a flip-flop for syncing the pulses into the microcontroller. And the microcontroller I'm using is an RP2040, so that's going to measure the time between two pulses, which will give me the RPM. Now this is the platform I'm using, because what I could do, I hook up a Bluetooth module like this. Now that will send the RPM data to my smartphone. So this is a platform I'm using so I can measure battery voltage, coolant temperature, oil pressure. So all those sensors are underneath the hood. Then it's sent by Bluetooth to my smartphone. So that saves me all the wiring from the underneath the hood into the cab of the car. So next we're going to have a look at the schematic diagram of my tachometer circuit. Okay, here's the schematic diagram of my tachometer interface. And the heart of the circuit is an opto-coupler. And you can see I'm using a 4N33. So when picking an opto-coupler, find a sensitive one with a 2-transistor Darlington output. Also look for a high CTR, that's current transfer ratio, In this case, the 4N33 has a CTR of 500%. So find one with 500% or higher. Now you can see my induction pickup on the very left. That's 4 turns around the coil wire. And that's fed into the opto-coupler with a 2.2K current limiting resistor. And I have a switching diode, a 1N4 and 4/8, that's clamping the reverse voltage. In case there's a reverse voltage across the emitter, it will clamp it to 0.6 volts. Then I have a speed up capacitor, 0.01, across the resistor. So the output of the opto-coupler has a little bit of filtering with a 10K pull-up and a 0.1 microfarad capacitor, and that's fed into a Schmitt trigger NAND gate, which is clean up the signal. So at this point here, you can have a very clean signal, pulse train, and then you could use it for wherever you want to do. If you want to go into a microcontroller, or if you want to put it into any type of circuitry. In my case, I have 2 more buffers, which is driving an LED for indication. Okay, so now that you have a nice clean pulse train, you could take that pulse train and feed it into your favorite microcontroller, and you could do a frequency to RPM conversion. So that's the signal that we got from the Schmitt trigger NAND gate. So the next part of this video, I'm going to answer a question that a friend had. He wanted to measure the distance between 2 spikes, and he fed that into the GPIO of his microcontroller, and he was missing some of the spikes. It wouldn't detect some of them because they were so narrow. So on a fast microcontroller like an RP2040, it would probably work. You could use an interrupt or the PIO, but I think he was using the Arduino. So this was the solution, and you could use this on any microcontroller. So here we have a D flip-flop, a 4013. It's edge triggered, positive edge triggered, the clock on pin 3. So it's sitting there waiting for the spikes right here. So as soon as it sees a spike from 0 to 1, whatever is on the D will be latched over to the Q. So now the microcontroller has all kinds of time to sense it because it's latched. And as soon as it senses the spike, it's going to send the pulse to reset the flip-flop. So the Q will go back down to 0. So that way, the D flip-flop is always looking for the spike, and it will detect it every time and give the microcontroller enough time to sense it, and then give back an acknowledge back to reset the flip-flop for the next pulse. So this is a circuitry I'm going to use just to show that it works, so we could obtain the RPM from the pulse train. Okay, I have TerraTerm up and running on my computer, and it's connected to my RP2040 microcontroller. So I'm going to run a program that will measure the distance between 2 pulses in microseconds. I have a microsecond tick timer running. So the program is called TAC, and I'll run that many times. So I'll run it and energize the coil. And you can see that's in microseconds, 3,200 microseconds, so that's 3.2 milliseconds. So next we'll look at RPM, so clear the screen. And the program is called TAC3, and do that many times. So we'll run that, and that will give us RPM. So it's about 9,300 RPM, so it's close to 10,000. So that's how we measure the time between 2 pulses in microseconds, and then we could calculate the RPM. Okay, I have my HC06 Bluetooth module plugged into my breadboard, and I have a program running where I'm going to pair my program to the module, and watch the LEDs will go solid when it's paired. So it says connected. So there's my sensors. My first one is TAC. So I'll run my simulator. And there's my TAC values sent over by Bluetooth. Okay, here's a quick look of a TAC circuit that's connected directly to the coil to the negative side of the primary. And it has a clamp circuit, an opto-isolator, and a Schmitt trigger NAND gate to filter out all the noise to give us a clean signal. And if I turn on my simulator, it's going to activate it, and the final pulse train will activate this LED. You'll see it come on. So the pulse train that's feeding this LED is clean, same as the first circuit. Okay, here's the schematic diagram of the tach circuit that's connected directly to the coil, to the negative side of the primary, which is connected to the points. So here's our coil, and you can see the plus terminal is connected to the battery, minus terminal goes to the points, and we're going to tap off that negative terminal into a 1N4007 diode. Then we're going to go through a clamping circuit, a 5.1 volt Zener. It's going to clamp this point at 5.1 volts, and we're going to feed that into the opto-isolator, which is an HCPL3700. Now the output of the opto-isolator, pin 5, has a little bit of filtering, 10K and 0.047, and then that output is fed into the 4093 Schmitt trigger and AND gate, which will clean it up, and we'll get a pulse train, which is feeding our indicator LED, which will be very clean. Now the voltage that we see on the negative terminal looks something like this. So when the points are open, we're going to see the battery, say set at 14 volts. Then the points close, it's going to ground the negative terminal, and it's going to build up magnetic field in the coil, and this is our dwell time. Then when the points open, we're going to get a big EMF spike. It's going to go up, we're going to get ringing, and then it's going to go back to 14 volts. So this is what we got to filter out all the noise in the high voltage and just look for this pulse here. That's what this circuit does. So then we could calculate RPM. Okay, here's the inductive pickup on my classic Mini. So here's my coil, ignition coil, and here's the wire coming out of the ignition coil, and here's my inductive pickup, 4 turns around the wire, and I got it hooked up to a connector so I could disconnect it. So I have another connector that fits in here, so you just plug it in like that, then you could run that into the tach circuit.